So welcome everybody. It's lovely to virtually see you all again. This is our 13th Talking Crystal Growth and Design webinar. As a reminder, this is a monthly series showcasing some of the most innovative researchers in our field. My name is Johnathan Steed. I'm the Editor-in-Chief of Crystal Growth and Design, and I'm joined by my co-host, Len Barber of Stellenbosch University. Thanks very much to the American Chemical Society for supporting this series, and particular gratitude to ACS Marketing Manager Emma Headington, who's really set everything up for us. We're just the spokespeople here today. So just as a reminder, later this month on on Thursday, the 24th of March, same time, we've got Jim Wiest from the University of Montreal. We'll be talking about exploring polymorphism, co-crystallization, and mixed crystallization. Should be really good. I'm a big fan of Jim's work. But the main event today is Professor C.Malla Reddy from the Indian Institute of Science, Education and Research in Kolkata. So let me just introduce Malla to you, although he needs very little introduction. So Malla's PhD was in supramolecular chemistry and crystal engineering from the University of Hyderabad in 2006. He then spent some time in Germany as a postdoctoral fellow at the Karlsruhe Institute of Technology between 2007 to 8. And then he joined IISER in Kolkata as an assistant professor, rapidly making his way through the ranks through associate professor, and has been full professor there since 2019. In 2014, he was awarded a prestigious Swarna Jayanti Fellowship by the Indian government. Malla's interests are in self-healing crystals, flexible functional materials, solid-state pharmaceutical chemistry, and structure mechanical property relationships. So as Malla gives his webinar, please feel free to post questions in the Q&A, not in the chat, in the Q&A, and we'll read them out to the speaker at the end. And just a reminder, we're recording the webinar, and we'll make the recording available afterwards, and you'll get a link to that if you're somebody who signed up, as you obviously are. So without further ado, Malla, let me invite you to give your webinar, Adaptive Smart Materials, from Mechanical Bending to Self-Healing. Malla.
Yeah, thank you very much, Len, and John, for the invitation, and also Crystal Growth and Design for inviting me. Let me share my slides. Yeah. Can you see my slides? Full screen?
Looks good.
Okay, great. Thanks a lot. Yeah. Thank you, John, for a nice introduction and also for the invitation. And I thank Crystal Growth and Design, starting this webinar series, which is basically very timely, and it keeps all the crystal growers and then crystal engineers connected. And then, so I'm glad to basically, give my presentation on adaptive smart materials. And mainly I'm going to talk about the mechanical aspects of crystals. And then I will slowly move on to the self-healing, which is a new phenomenon that we have been seeing in the literature, and this is basically there in the literature in other materials, but only recently, we started looking at, and there are only a couple of groups working on self-healing. But I believe that self-healing is actually probably common, but we have not basically, we have not done enough to see this in many materials. But I hope this will basically grow very rapidly. So before going into the details, so I thank all my present students, PhD students, and former group members, and then all the collaborators. Without them, we would not be able to do so much, and the funding agencies, and then IISER Kolkata for all the facilities, and then Christinchcom and AFTAB. I'm associated in the editorial board, so I thank them for all their support. And so then I'm going to present the work mainly from some of these authors, but not limited to, and these are the main people we have contributed to the work that I'm going to present today. But definitely there are many collaborators and students from the collaborators who have contributed to this work. So, and also the many things that I'm going to show are from different groups. Just to give you a perspective, I'm going to present the literature, and then I try to cite as much as possible. So I try to just take you through this, field on the adaptive materials and then mechanical properties of molecular crystals. So we know that molecular crystals are normally brittle and they are fragile. But there are many crystals which respond to mechanical stress, and then we have seen many examples in recent literature. So I'm going to basically cover some opportunities and challenges that we see in the mechanically responsive crystals. Then I'm going to go into the self-healing material molecular crystals, and then I will also show you the challenges that we face in understanding self-healing crystals, and then I give you some insights into the mechanism of self-healing materials. So we know that molecular crystals have been there, and then people have been studying, and then we have 1 million crystal structures in the CGD, and we have more than 1 million now. So mostly if you look at the literature, and the crystallographers, particularly crystal engineers, have tried to look at crystals mainly for the structure solution, and then to understand the structure and then property correlationship, and then look at the intermolecular interactions and various kinds of intermolecular interactions. So we have been traditionally looking at only good crystals, and anything that is not qualified to be called as good has been rejected, right? So then what happened to those crystals which were not really good for the crystallography? So since we are interested in mainly the crystal structure, and people wanted very good diffraction pattern, because that gives you very good structure, and then you will not have any problem in understanding the structure. So people have been basically ignoring all the crystals that were not very good in terms of crystallography. So if you have a crystal which is not very good in terms of quality, so that would normally give you complicated diffraction pattern. So you don't want to deal with those kind of crystals, right? So, and for example, if you have a crystal like this, you will be actually, in olden days, you would be very disappointed. But now that we know many crystals which are very useful, for example, if you have soft crystals, so you can study them for different other purposes. So we will be actually delighted. So these crystals which were not very good in terms of crystallinity are now actually wanted crystals, I would say. So then how did we get into the mechanically bendable crystals, for example, the soft crystals? So people actually have seen earlier in olden days also the crystals which were not very good or curvy type, but people generally ignored them because, as I said, people were interested mostly in the structure and crystallographic information. So people ignored. But in 2005, when we got this results on some mechanically bendable crystals, for example, if you can see here, so these are very simple crystals. When you bend them, so they basically bend mechanically, and then this is a plastic bending. And here, if you look at the structure, so these crystals have slip planes, and then you have some stacks, right? In between these stacks, you have weak interaction planes, and these weak interaction planes actually allow you to actually slide these layers, and that is how basically you have mechanical bending, plastic bending in these crystals. And then later, we also looked at the elastic crystals, and again, people probably have seen elastic crystals, and also in other materials, elasticity is very well known. But in case of molecular crystals, particularly from the structural point of view and from the crystal engineering point of view, people have not studied with purpose to understand elastic bending. And then I would say that this was one of the earliest examples where detailed structure mechanical property studies were attempted. And then now we have many examples from groups, and then earlier. So just to summarize this, so people normally believed in olden days that molecular crystals are brittle and then fragile, like as you can see here. And then later, then we have seen flexible crystals with elastic bending. For example, as you can see here, this is a caffeine co-crystal, and it beautifully bends when you apply the mechanical stress, and then when you release the stress, so it actually goes back. And when it breaks, as you can see here, so the two pieces basically again regain their shape. If you put them on diffractometer, they give you beautiful structure even after you play with them and then release the stress, so they spring back. So these are elastic crystals. And then you have plastically bendable crystals, as I said. So these crystals don't recover, and so you can actually bend them into different shapes. And then now we have many examples and dynamic crystals. For example, so these are from Hayashi from Japan. So as you can see, this is an elastic crystal with beautiful luminescence. And then you have metal organic crystal coordination complex here, the crystal of coordination complex from Mariana, and then this is from Francisca. And then there are other people like, Zhang, and he has shown that, you can even twist the crystals, and then you can also have elastic bending. And then we know very well these, thermosalient crystals from Naumo's group, and then they also have shown applications of various types of mechanically flexible crystals. And then from Ito's group, then fluorescence and many other properties have been shown. So then you have, J.J. Whittle's group, where they showed the photochemical reactions, and then mechanical jumping, and then there are many other examples. I just showing you the different representative examples, but there are other people who have also contributed to some of these. So as you can see here, so the crystal actually develops a twin domain, or sometimes a different crystal form, and then you can basically go on doing many things with the crystal. You can twist, and then you can bend with the light. So this is from our group, from my student Ranita. So here you have a polymerization reaction on the inside in the crystal, so that actually contracts the unit cells on the inner side. From the side you are shining the light on the crystal. So this allows you to actually have the photomechanical bending. There are many other examples, 2+2 reaction from IISER and many people like so there are many examples on the photomechanical bending. So then but then if you look at actually most of the molecular crystals bend on, for example, if you have plasticity, in the literature people have shown that if you bend those crystals plastically, they bend on one face or on the two face, but if you try to do anything else, they will simply break. For example, if you take a copper wire, unlike molecular crystals, plastic molecular crystals, so you can twist, you can basically make a thin film, so they are very ductile, right? So for example, highly plastic metals, when you go to higher temperatures particularly, so you can shape them into any shapes, but that was not seen in the molecular crystals. Although people have studied certain crystals which are called plastic crystals, so where you have orientational disorder in the solid state. So people have shown that those kind of crystals actually show extreme ductility and malleability, but structural property was not actually again looked at from the crystalline point of view. So as you can as you can see here, and this is a very simple aminoborane molecule, and when it crystallizes at room temperature, you have a phase where you have molecular rotations in the crystal. So these traditionally these are called plastic crystals, where you have orientational disorder, and people call them as plastic because most of these crystals with orientational disorder in solid state, when you go closer to the melting temperature, they showed extreme plasticity. So that is why all these crystals with orientational disorder in olden days, like 70s and 90s, so people have called them as plastic crystals. That doesn't mean that only these crystals with orientational disorder are plastic. This is a little bit confusing, but people in those days just found them as plastic. So as you can see, you can pull this crystal like a copper wire, right? And you can also compress these crystals, and then you can even thin these crystals by applying the mechanical force, and then you can even put these crystals, and then if you push them, so they stick to each other very nicely. Okay, very little stress is enough, but if you want to do it quickly, so you just compress them little hard, and then you see that they beautifully get compressed, and then they get attached to each other. So this is very unusual for molecular crystals. So we studied these crystals, and you can look at this paper. So we see that you have molecular rotations in these crystals, so that is why they are plastic. So by definition, you can call them as orientationally disordered crystals or plastic crystals. So what are these plastic crystals? So people have actually looked at these, as I said, in 1970s. So Timmerman studied them and then actually gave certain kind of conditions under which they actually form plastic crystals, and then they also describe the physical properties of plastic crystals. You can look at this beautiful book by Sherwood at Strathclyde now, I think. So so here, as I said, you have a lattice where you have long range order, but locally the molecules actually have short range order. So that means you have orientational disorder, but you have a long range order. So since you have long range order, so they give actually good diffraction pattern. And then these crystals also have many advantages. And then if you compare them with the other types of molecular crystals, for example, if you have highly ordered crystal, okay, so you have highest order and you have least molecular motion actually in the solids. So these are called ordered crystals. And then if you have orientational order, but you have a long range order, so you have good long range order, but you don't have local order. So you call them as basically uh, glassy crystals, where you actually don't have dynamic disorder, but these are actually frozen with random orientation. So then you call them as glassy crystals. So, but these have good long range order, but they don't have local order, but these are not dynamic. When they are not dynamic, when these are frozen in different orientations, so you call them as glassy crystals. So this looks like, you know, oxymoron, but it has both the properties of glass and then the crystals. So then you have amphidynamic crystals, where a part of the molecule actually is dynamic. And then you have plastic crystals, where you have long range order, but you have dynamic disorder at the local level. Molecules actually rotate along one axis or multiple axes, or, you know, or sometimes they are even, particularly when you go closer to the melting point, they're actually isotropic. So then, since they're isotropic, you mostly have at higher temperatures, you have high symmetry crystals, and then they are highly plastic. So then you have liquid crystals, and then you have isotropic liquids. So if you go this, when you go this side, so you have more motions, and then on this side you have high order. So here you have crystals, perfect crystals with perfect order, and then you have isotropic liquids. So in between you have various types of interesting crystalline forms or materials which have both crystalline order and then also certain amount of motion in these two. So then soft crystals, probably you can put it with the order crystals, because you have order, but they are not maybe on this border where they are actually between glassy crystals and shear. So when you apply mechanical stress, sometimes they lose the local order. So I think you can place them here, but they are still, most of them are still in the ordered crystals. You can put it, you can look at more details here and the applications of these plastic crystals. So as I said, if you take ordered crystals of certain molecules, where either you have spherical shape, if your molecule is spherical or cylindrical or flat sometimes, so when you heat them at beyond certain temperature, so they attain these dynamic motions, and then they will give you plastic crystalline phase. And then when they go to plastic crystalline phase, since when you basically melt something, then from the order phase, they directly go into the melt phase, then you have all kinds of rotational degrees of freedom. So you have a big entropy of entropy change or enthalpy change, right? So then when you basically have ordered crystals going into the plastic crystals, in the solid state, you have orientational motions. So this takes a lot of energy, right? So when you go from ordered state to the disordered state, then you have high entropy change here. So this hump is very, if you look at normally in the DSE, so you will have a big peak here, and then subsequent one, including the melting ones, would be normally below this, lower than this. So this tells that you most probably have plastic crystalline phase. So this is a very good technique actually to figure out if whether you have a plastic crystalline phase or not. So then most of the time entropy of fusion. So entropy of fusion is, if it is a very good plastic crystalline state with orientational disorder, you have less than 20 joules per mole per kg for the material. So, and this tells you that, you know, if you have a smaller hump here in the DSC, so you should actually check for the existence of plastic crystalline phase. So then if you have one molecule which is fully which attains complete rotational degrees of freedom, normally your delta SF, that is, you know, entropy of fusion change is actually less than 20 joules per mole. And if you have two species like, you know, cation or anion, if only one of them is basically rotating before the melting, then you are basically, this value goes up. And then if you totally have an ordered phase, then basically you have a very high entropy of you know, fusion. So you can look at all these details here, and then these plastic crystals also have many applications. And so, for example, if you look at some perovskite crystals, and so here you have a guest which attains orientational disorder before melting, and then you can use actually this energy change for cooling the, you can use it as a coolant, solid coolant. So this can actually replace the liquid coolants that we use in the refrigeration technology. So then here we found a crystal which is actually in between the plastic crystals where you have orientational disorder and static crystals where you have 1D or 2D plastic bending or elastic bending. So we always have, in the literature, if you look at carefully, so plastic crystals, traditional plastic crystals where you have orientational disorder, and then plastic crystals where you have static disorder, but because of slip planes in one or two phases, two directions. So in both the cases, you will see the plastic deformation, but the difference between these two or connection between these two is not very clear. And so this example was very good, and we actually could see both orientational disorder at high temperature and plastic and elastic bending at the room temperature. So as you can see here, this is actually, it does not have orientational disorder at the room temperature, but when you try to bend this crystal, initially it is elastic, and then when you stress it further, so at some stage it actually becomes plastic, but still it shows both plastic and elastic deformation. For example, if you see here, so it does not recover fully, but there is some recovery, small amount of recovery. That means it is having both plastic and elastic nature. So that is why you call it as a elasto-plastic crystal. So that is why it is in between the elastic and then plastic crystal type at the room temperature. Then again, when you actually locally press it, and these long needle type of crystals, if you just press it at local level, so they also actually break, like more like brittle crystals. So to summarize this, these crystals at ambient temperature have static molecules. They don't have dynamically disordered molecules. They have static molecules. And then when you bend it very little bit, initially they show elastic deformation. When you bend them further, they show both plastic deformation as well as elastic recovery. When you break these crystals at room temperature, basically if you crush them, so they actually break into small pieces. So they actually undergo brittle fraction. So then when you heat them under above certain temperature, then you see molecular motions in the crystals, and then you go to a dynamically disordered phase or this plastic crystalline phase. And where if you try to bend these crystals, they are beautifully plastic. And when you try to basically compress these crystals, and then they actually become into thin sheet. So this is actually typical to the plastic crystals. When you go closer to the melting temperature, particularly, so they show high plastic deformation. So that is what we have seen here. So you have all kinds of properties. It is brittle to some extent, then you can actually have plastic deformation and elastic deformation at room temperature. Then when you go to high temperature, actually you can see that it is extremely plastic. So then we did the DSC for this. As you can see, this peak is actually much bigger compared to this melting. This is melting, and immediately after the melting, there is a decomposition. That's why you see a big hump here. So, but essentially, this melting peak is smaller compared to the solid to solid phase transformation, where you have order to disorder transformation. So that is why you have a bigger hump. This tells that this is actually a plastic crystal. And then we looked at the structure. So you have beautiful slip planes, but there are certain weak interaction here. Probably that is holding them to some extent, and that is where it is a little bit elastic. But if you push them further, so it shows plastic bending. Probably you have slip through these weak interaction planes in these crystals. So then we looked at actually on the microscope using the cross polarizer. So as you can see, at these phase transfer temperature, the crystals actually lose the iridescence. So this tells that because of the orientational disorder, so you lose the anisotropy in the local anisotropy in the form. So that is why basically they become almost like non-iridescence, right? So it becomes almost like dark. So you lose this. So this is a GIF file, so it is repeating. It does not mean that the crystals actually transform this way, but when you heat, then you lose the iridescence in both the cases, as you can see. So when you actually go to high temperature, and then thin these crystals, and then you actually see a big thin film kind of thing. So then when you look at it, bring it back to the room temperature, and then you look at it under cross polarizer. So you see that there are a lot of domains, right? So when you deform it, it's not single crystalline anymore, and then it actually has a lot of domains. So it becomes almost like a nearly polycrystalline in this particular case. So then we took a crystal and then we bent it and then did the heating experiments, and we see that at the bent region, the crystal actually loses the iridescence first. That means that is where these phase transformation actually happens before the other region. So this also tells that if you have a deformed region, so that is, it has more defects, so the packing also becomes energetically little goes into higher energy. So then it is less stable. So that is why you have phase transformation before the pristine region. And then we propose that if you look at the crystal packing, so you have molecules stacked in this direction, these are tetramers, and then you have weak interaction between them. And when you bend it within the elastic regime, so molecules actually here rotate in this fashion, and then the molecules in the outer side rotate in the opposite direction, so that you have elongation of the unit cells here because of the rotational. So this is a well-known elastic bending mechanism. You can see it in the literature. So then on the inner side, you have different orientation. So you have compression of the unit cells here, and you have elongation of shortening, and then elongation of the unit cells on opposite sides. So then when you push it further, then you have slip here, and then because of that, it actually shows the plastic deformation, but still you have the similar kind of orientation. So molecules actually relax a little bit. So that is why you probably have the elastic recovery even after you see some plastic deformation in this. So that is why it is elasto-plastic. Then when you go to higher temperature, basically it loses the elasticity, so it completely becomes plastic. So now I move into self-healing materials. As I said, self-healing is actually not very common in molecular crystals. It is probably common, but we have not explored it enough. So, but it was found in other materials, and it is also abundant in nature. For example, if you look at the bone, when there is a fracture in the bone, so this fracture surfaces actually develop electrical charge, and because the bone is a composite which has collagen in it, and the collagen has amino acids, and because these are peptides are made with the amino acids which are chiral, right? So since you have polar structure here, so all the polar structures are bound to be piezoelectric, right? So that is why bone actually has some piezoelectric or flexoelectric behavior, and because of that, when the bone fractures, so you have charges here, okay, potential electrical potentials, and then that brings the cells which actually come here and then deposit the minerals. So that is how basically the crack heals here. So this is actually self-healing, but this mechanism of self-healing is different from other mechanisms. There are a range of mechanisms in soft materials. So for example, if you look at in gels, there are many gels now which actually have been shown to show the self-healing. For example, if you look at here, so it has this is actually a gel of a polymer, and it has hydrogen bonding side chains. So it is proposed that this gel with a lot of liquids in it, and so basically these side chains, when you break them and then put them together, so these side chains actually form hydrogen bonding interactions, and then that is how they basically bring these two together and then allow the healing. So, and then there are other methods, and in the polymers, then people also have taken hydrophobic interactions with complementary lengths, like one is longer than the other, and then you have a longer one again. So this basically gives you a comb-like arrangement, and then when you cut a polymer, and then after some time you see that these polymers actually come back and then again pack because of these van der Waals interactions. So this actually allows the self-healing here. As you can see, these are all very soft materials, and these polymers are really soft, and so most of the self-healing materials have been shown to be very soft. So if you look at self-healing in soft materials, and mostly it involves self-healing involves stimuli such as heat, electricity, or humidity, and sometimes light, solvent, and so on. You need some stimuli most of the time. And then these materials also require diffusion. Okay, because most of these are soft materials, can easily diffuse the material inside, and then they have some dynamic bonds or chemical reactions sometimes, and it works when broken parts are actually put in contact. So when you break something, you should allow them to be actually in contact. If they are not in contact, so normally you don't have any self-healing in those materials. So but why self-healing is actually challenging in crystals? Because crystals are actually very stiff and rigid, and diffusion is also very difficult because these are densely packed materials, and then they have very tight interactions. So you have a close packing. Because of that, diffusion is very difficult in molecular crystals. And then fractured crystals break into many pieces. Normally you don't have a very clean surface where when you put them together, so they come, and then since they're also rigid and solid like, so you cannot really close this gap properly. So that is another challenge. And then probably there are methods using which we can actually induct self-healing in molecular crystals, but there are not many systematic studies. And then characterization of self-healing itself is very difficult, because how do you actually probe the crystallinity at the fracture junction? Because you need to have a technique where you can actually really probe the crystalline order, because when you have crystals, so the main property of the crystals is its order. So characterizing the order at the nanometer scale is a very big challenge. So that is why it is not very easy to actually study also. People should appreciate that. And self-healing is single crystals. For example, if you look at, there are examples. And for example, if you look at, this is a protein and polymer hybrid, and it has a lot of solvent voids, and then you have a lot of solvent here. And if you put these crystals, as you can see here, in a salt gradient, actually, and if you change the salt gradient, these crystals actually can expand and then shrink. In this process, they develop cracks, but these cracks with time actually heal. So this is actually polymer and protein hybrid crystal, and you can see nice healing of the cracks. But this entire thing happens in the solution. Okay. And then we have other examples in molecular crystals where you cut a crystal and then you put them together, and then time, so they come together and then they heal. So in this particular case, this was first example in molecular crystals. You can see that the healing is 7%. It actually regains some mechanical strength. And then there is another example. You can see better healing here. And these crystals are, again, this crystal is very, very soft. You can see the crack here. And so, but still this holds the crystal together, and then it regains the mechanical strength. But here, what is the crystallinity at the junction? Whether it is highly crystalline or it loses the crystallinity. So that we need to look at. But and this itself is actually important, because we don't know much about the self-healing in crystals. So then we were looking at some of the crystals in our lab, since we are interested in the mechanical properties. So my student was studying these crystals. Then we found that these crystals are brittle. When you basically apply the mechanical stress, they break. And these are also very hard and stiff. You can see 8 to 15 GPa elastic modulus. And these are like, long needle type crystals. But when you apply the mechanical stress gently, and my student Surajit found that, and these crystals break, and then they heal the crack very efficiently. But when you push very hard, and then this crack does not heal properly, as you can see here. Here, you can see that the crack remains when you push them very hard, but when you push them very gently, most of the time you see that the crack heals completely, and you can't actually find any sign of the crack that existed there. And this is another video where you can see you have a big crack here, and then it's gone. When you release the stress, this is a slow motion, and you have a big crack here, and then after you allow it to heal, and it does not heal all the time, but when it heals perfectly, you don't see the crack at all. So then we were wondering how these crystals actually come back when you release the stress. For example, if you look at here, so this was broken and you have a crack here, and then you basically pull back your metal pins, and you see that this crystal actually jumps, right? So there is some force here. So that is what we realized. And so these crystals are able to come back on their own, and there must be some kind of a attractive force here. So then we took a crystal and then broken it into two pieces, and then we pushed from one side, and then we found that there is actually an attraction, and then this piece would jump, and then it will actually go and get attached to that. So this tells that there is a very strong attraction, and this is about 50 micrometers. So this is quite far for crystals to actually attract, right? So that tells that there is strong attractive force. As you can also see here, you crack these crystals and then pull back your forces, so they come back on their own, and then they actually heal. So then we had to really go into details, because we had no clue why these crystals actually come back and then attract, and then we did not know what was going on. So as you can see here, you push from the top, and then these crystals also recover of this. You have a big crack here. This is, I think, more than millimeter width. Width is actually more than a millimeter. And so then we basically looked at the SEM, and then when there was a perfect healing, we did not find any sign of the crack. And mostly we found that when the crack is linear and it heals very good, when the crack is not linear, so we found that, or when you have some debris in the middle, so you don't have a very good healing. So, and what is the origin of the self-healing? What is the origin of the attraction? So then we went into the details and then looked at the structure. We found that this is a polar crystal, and this is the piezoelectric crystal. And then we basically looked at the literature, and from piezoelectric crystals, we know that when you apply the stress on the crystals, so then you have disbalance of the charges, and then opposite faces actually develop the potentials, right? So then on one surface, if you have negative charge, on the other one you have positive charge. So this is common in the piezoelectric materials. So then we wanted to characterize the piezoelectricity and understand what exactly it is. So then we have done PFM, and with my collaborators from IIT Kharagpur, and then they looked at actually PFM on the single crystals, pristine single crystals, and also broken single crystals. My student has done these measurements, and then we found that on pristine crystals you have better D effective value compared to the broken crystals. So these are not really pristine anymore. So we see that their performance, piezoelectric performance actually goes down a little bit. And when we also use the piezometry on the bulk crystals and the pellet, we see that on the bulk crystals, pristine bulk crystals have slightly better property, piezoelectric property, compared to the pellet. So this is understandable. When you compress the material, so you might actually deform them plastically. So that might actually give you some kind of a history. Basically, that might have some impact on it. So then how do you understand the charges, whether there are really charges on the crystals? So then we broke a crystal, and then we, using KPFM, Kelvin Probe Force Microscopy, we mapped the surface. Then we found that some crystals have positive potential, and then some actually have negative potential. So depending on your orientation of the crystal, then polar axis in the crystal, because these are polar crystals. So when you break it, you might either have positive charge or you might have negative charge. So then we also looked at a crystal. We cut a crystal. We basically broke a crystal, and then there was the healing was not very efficient in this case, where you can see a crack. So then we mounted this crystal and then tried to map the surface, and then we found that here one part is negative and the other part is actually positive, as you can see. So in piezoelectric ceramics, so crack junction has been studied by people. They also found opposite charges across the crack line, right? So then we propose that when you have a polar crystal and then when you break it, so you have attractive charges on the opposite surfaces, because these are polar crystals. So you have tail on one end and then head on the other side. So they should have opposite charges. So then that might actually allow the charge generation on the surfaces, and that allows the crystals to actually come back and then heal. And as you can see, you can look at this paper. So there are examples where you have a crack. So people have shown that this kind of opposite charge generation is actually not new. in the materials. So then we wanted to understand, once you heal these crystals, how good they are. So are they really single crystalline in nature? What happens to the local order in these crystals? So then my student Somnath did the analysis of single crystals. So we took a crystal and then allowed it to heal perfectly, like where we did not see any crack after healing. And so we mounted these crystals, and then we found no sign of actually deformation in the peaks. So these peaks looked as good as the peaks from the pristine single crystals. But when the crack was visible, for example, when the crack was visible like this, and then when we mounted these crystals focusing here in the middle, we found actually split peaks. This tells that these two domains are actually misaligned. When the crack is visible, when the crack is not visible, the two domains are actually perfectly aligned. Again, since the X-ray is an averaging technique, right? So you cannot actually give the local order information about the local order. So then we talk to our colleague who works on the Mueller matrix microscopy. So here, using his technique, he can actually look at the polarization of the light that comes out from the crystals. So then he found that the pristine crystals had the highest order parameters, and then the neatly healed crystals also had very closely, the order parameters were very close. But when you had the crack, visible crack in the crystals, so you could see that the order is actually many times lower. So when you see the crack, so the local order is actually gone, and the crystal basically loses the crystalline order. And but when the cracks are not visible, so this is as close to as possible to the pristine crystals. And you can also look at here. So in the crack junction, we did not see any drop in the order parameters. So, but when you have a cracked crystal with this crack, so we saw a big change here. So this tells that this technique is very good because you can actually probe it at the nanometer scale. So here the resolution of this technique is around 300 nanometers. So we could see and understand that, you know, in the healed crystals, your order parameters are actually very, very good. So then we basically looked at the efficiency, and it tells that neatly healed crystals have 85 to 90% efficiency in terms of the local order, not in terms of property or other parameters. But when you have a crack, so you have actually around 50% order. When you break the crystals into two pieces and look at one, in that case also we had 80 to 85%. So this tells that there is some kind of a plastic deformation or some kind of a hysteresis in the strain in the crystal. So that strain probably distorts the dipoles. And then as you can see here, if your material is highly elastic, so when you deform it, you have opposite charges. But if it is highly elastic, then it would actually recover completely. But if it is not totally elastic, so you have small plastic deformation, and then you will still see some kind of a remnant charges on the crystals. So that is what we actually propose, and that is why we think we have the opposite charges on the crystals. So with this, I conclude soft crystals are attractive for various applications. I think self-healing will be a phenomenon to explore in molecular crystals because that can give us many opportunities. And polar crystals are ideal for exploring self-healing. And self-healing is again difficult to achieve in hard materials. And so the mechanism that we showed probably will actually allow us to design molecular crystals which are hard, highly crystalline, but still show the self-healing. Yeah, with this, I thank all of you for your patience. And I think if you have any questions, so I'll be happy to answer.
Well, thanks so much. Absolutely fascinating. It's an area of chemistry where the videos say everything. I mean, I've heard of the phrase, a picture says 1,000 words, but in this particular case, that the video really is everything. It just completely defines the field in some ways. Okay, so we've got some questions appearing in the Q&A. If you have questions for Malla, please do put them in the Q&A. So we've got a couple of questions from Philemon Mugani, who was asking about generally the interaction of these crystals with the atmosphere, and then specifically in the context of atmospheric gases and even combating climate change. Is there an effect of the atmosphere, I suppose, versus being under a liquid medium on the behavior of the crystals?
Yes, we see some atmosphere change, effect of atmosphere, and we are right now looking at some of those properties. Definitely, it has some effect.
Thanks. Okay, and then anonymous, nice talk. You have a video showing self-healing of two pieces together. As I can see from your presentation videos, self-healing behavior is only seen when you generate a small crack. If you remember the phenomenon in superelastic crystals at Takamizawa, where tiny cracks appear and they immediately disappear when the pressure is released. I would say the self-healing phenomena which you've shown here is something similar to that reported in superelastic crystals. It also supports that no clear healing is observed when there is no crack formed straightly. If at all, it's a healing that should not be following such patterns. What do you think?
I think there might be many ways through which self-healing can happen in crystals, and but if you need to have attraction, I think you need charges, and if you need charges, then there should be some kind of a symmetry breaking in crystals. So, I think self-healing probably when they see the cracks. Okay, in many cases we see the cracks and then they disappear. So in other materials, the same phenomenon is called self-healing. So I think we need to look at closely and need to really understand what exactly is going on in those cases. Yeah,
Great,
I think we need to take these very small observations into account and then look at them more carefully. I think then we will probably know many things.
Thanks. Okay, and a question from Panche Normov, one of our previous speakers. Hi, Panche. Have you determined the ultimate tensile strength of the pristine crystal versus a healed crystal?
No, we couldn't do that. We tried to do that, but we couldn't do it. And also we tried to do some 3-point bending tests on these crystals but we could not succeed because we didn't get very reliable data. Because once you break these crystals, so they actually actuate. So that was giving us a lot of error. So that's why we could not actually do the 3-point bending. And we don't have a good facility to also do the tensile test. But the problem here with the tensile test is when you hold the two ends and then you allow them to come together. So you are basically restricting them to align on their own when they are free. So because they have charges, so they come back and then try to align themselves and then they stick to each other, and that would give the better healing. But if you hold two ends and then put them together, they stick to each other probably, but they don't properly heal. So, but I would expect that these crystals may not show complete recovery in terms of mechanical strength, because we see that when you poke a crystal at different locations, once you have a crack in one place, although it shows that it is healing completely, it actually cracks at the same time, irrespective of where exactly you poke it. So that tells that that is actually the weakest plane in the crystal, and then that tells that this is not 100% healing definitely. But that would be interesting. But there are some difficulties to do it because these crystals are not very big, and but I think we have not spent much time on that. We are going to actually look at some of those. Thank you, Panche.
Challenging, thanks. Okay, we have a question from Swapnendu Pramanik. If we apply pressure from different angles, will there be any changes in the self-healing percentage?
See, in these crystals, the polar axis is actually perpendicular to the needle axis. And so that we could do easily because of the shape of the crystal as well. But we are looking at some of these aspects in other crystals where we have kind of a plate-like structure, plate-like morphology and other morphologies. So we see the influence of angle at which you actually poke the crystal on the self-healing.
Great. And Dinesh Kumar says, a wonderful lecture. There's a lot of scope in this research in pharmaceutical materials, especially in tablet manufacturing. Would you care to comment on that? I think that the paper I put in the chat of yours actually was on that topic, wasn't it, that you had recently in crystal growth and design?
Yeah, so that was basically not a self-healing material, but that was on the mechanically deformable crystal, where we showed the influence of mechanical properties on the tabletability with Kelvin Sun, who is a good friend of mine, must be here in the audience. So definitely, I think these materials also might have effect on the way tablets form. So we are looking at some of those aspects as well.
Okay. And then a question from Avantika Hasija. Can you comment on the surface rugosity at the cleavage site in self-healed crystals?
Yeah, I think rugosity at the molecular level, I am not sure how that is going to affect, but at the level of the macroscopic piece, that is definitely going to actually have some impact, because if the crystal, when the crystal actually is broken and when it is approaching the again back, so if it is stuck in one location where you have a kink, so it may not be able to go back. So at the macroscopic level, I think surface rugosity definitely would have a role, but at the microscopic level, I am not sure, because the charges will be able to overcome if there is any slight hump in the crystals.
Okay, we're getting a little tight on time, but maybe we've got time for two more questions. So Philemon Mugani asks, are there some crystal lattice imperfections, and has machine learning algorithms solved this problem? I guess the understanding of the lattice imperfections.
No, I don't think anybody has looked at these crystals using machine learning and other computational tools. But definitely, I think this is going to be a topic of interest in the future. So lattice imperfections definitely have a role on the charges that are generated in these crystals. But again, we have to study more to really, provide the proof for atomic or molecular level imperfections in the crystals.
Okay, great. And I think Pancho's got a follow-up. He says, according to your explanation, elastic crystals have isotropic interactions, interlocked, while plastic have anisotropic interactions, slip planes, based on theoretical results without experimental results of bent section. However, there are only two examples in the literature where bent parts of the crystals were analyzed using microfocused X-rays, and he gives the citations. Based on their experimental data, elastic crystals have anisotropic interactions instead of isotropic, and plastic crystal doesn't have any slip planes. Can you comment on this?
Yeah, thank you, Pancho, for asking this. So see, the isotropic nature and anisotropic nature is a very qualitative one. And when we say elastic crystals are isotropic, it is totally a relative term. When you say plastic crystals are anisotropic, again, this is totally a relative term. But if you look at all the crystals are actually anisotropic, depending on how you look at, right? So you will always see anisotropy in the crystals. So here again, coming back to the presence of slip planes and interlock packing. So initially, we definitely proposed interlocking could be one of the main features. But interlocking again means either it is mechanical interlocking or it means energetic interlocking. It is all a barrier that we wanted to actually suggest. So slip plane is again, what do you mean by a slip? So any plane along which there is a slip is a slip plane. That doesn't mean that the layer has to be really flat with the molecules at the molecular level. So all the plastic crystals actually have slip planes. But people have not defined these properly. We are writing a paper on that. So you can also have a slip plane like this, but it is easier to move them this way. Okay, you cannot move this way. So if you have molecules, I hope you can see my hands. So if you have a plane, so in this direction you can move, right? And but you cannot move in this direction. So this is actually a slip plane, although you don't have flat molecules. And then coming to the Clegg's argument. The mechanism of elasticity, the molecular rotations, so they have given a correct representation, although molecular rotations were always considered for the elastic bending, but people have actually did not get the right, on the outer and inner side, they did not get the right mode of the rotations. But the copper acac, if you look at, again, there is a paper which is in the archive, Chem archive. You can go and look at it. I'm sure you must have seen. So copper acac is not totally an elastic crystal, and although the authors originally also mentioned that this is elastic within 1%, but then the entire story on its plasticity is actually not studied in detail. So that is why we easily get confused with the structural aspects required for elasticity and plasticity. So here we need more clarity. And so I think if you look at that K-Markai paper, you will get some answers. So, but still regarding the interlocking, so we need to understand it in much more detail, both in terms of computational techniques as well as from the topological, arrangement of the layers. So I hope I'm able to at least answer your question partially, because we still don't have full answers. But if you look at, I have clear understanding that all plastic crystals have slip planes, but not the flat slip planes. But anisotropy and isotropy is kind of misunderstood. This is totally a qualitative term.
Great, thanks. We've still got maybe 4 minutes left, so maybe one quick one. Amila Abisakera asks, is it common or the norm that plastically bending crystals only bend along one face, but elastically bending crystals will be able to bend along two faces?
Okay, see, generally the plastically bendable crystals also have been shown to bend on both the sides. There are some, it depends, like, whether you have slip planes in, aligned with one face or two faces. So there are many examples where you have one face plastic bending. There are examples where you see two face plastic bending. In case of face plastic bending, you also normally see the twisting. But then these plastic crystals where you have orientational disorder actually can be they are highly malleable. You can actually deform them in any orientation or in 3 dimensions. So elastically bendable crystals, I think if you have exactly the same thickness, most of the time you may be able to see elasticity on both the faces, but it is not necessary that all the examples actually have two-phase elasticity. So it depends on the internal structure. For example, if you look at copper agate, it is highly elastic on one of the faces, but it is also equally elastic and plastic on the other face. So we cannot really say. So it depends on the structure.
Well, I think you can see, Mueller, that you've really sparked people's interest here. The questions are still coming in, but we're getting a bit short on time. Maybe I can just ask you, on behalf of the sort of younger people or emerging researchers in the audience, how is it you go about identifying systems that have these kinds of behavior? Do you just try lots of crystals, or do you have some insight into what to look at in order to identify the systems that you've shown us?
Yeah, so see, there is always some kind of a empirical exploration, definitely, but that doesn't give you enough you will not get enough example if you purely follow that. So what we do is, from our understanding, it is clear that if you have more hydrophobic surfaces on the molecule, you are likely to get soft crystals. Okay, so then we have also seen that if you have a molecule and then on either ends, if you have van der Waals groups like methyls or tetrabutyl groups or chlorines, so most of the time they form slip planes in the crystals, so that would give you the plastic deformation. So we have a paper on that in JACS, I think that was in 2015, where we have shown in totally unconnected systems that when you have hydrophobic groups on either ends of the molecule, if you take a relatively linear molecule with hydrophobic surfaces in the middle, or even if you have small hydrogen bonding groups, like relatively less hydrogen, groups less prone to form hydrogen bonds with hydrophobic groups on either ends. So we have seen that many of them actually form plastic crystals, plastically bendable crystals. So we know something already where we can attempt crystal engineering, but again the success rate is reasonably good, but as with all the crystal engineering attempts, so we have some trial and error as well here.
Great. Okay, well I guess we're out of time, so perhaps we're going to bring proceedings to a halt, but let me thank you on behalf of all the 150 attendees we've had, Mueller. That was an absolutely fantastic talk, really fascinating to watch as well as to listen to. Really appreciate you got off to a fantastic start for our 2022 series, so thanks ever so much.